concept of the two-stage acoustic non-invasive monitoring and diagnostic system based on deep learning. In industrial predictive and prospective analysis, one of the most important directions in Industry 4.0, where machine monitoring in diagnostics is a critical part of its operation. Currently, there are systems in the world that monitoring rotating machines with vibration sensors or acoustic emission analysis systems. The process of automatization of the collection and analysis of information is becoming more and more critical, increases the speed of the response to changes in the process and condition of the equipment, and the low cost of the technology used is also important. These are the requirements that the solution for non-invasive acoustic monitoring and diagnostics under development must meet. Non-invasive acoustic data gathering is particularly interesting because of high ergonomics and low costs. The general method for processing such type of data is anomaly sound detection. This method allows express diagnostic and monitoring of machines and units with minimal integrations. The goal of our work is to develop a system of two-stage monitoring and diagnostic for rotation machines by an invasive acoustic method with the following validation and verification of results on the experiment stand. The basis for a correct analysis of the condition of the equipment is valid data. Therefore, quite strict requirements are imposed on microphones. Acoustic analysis with microphone has strict requirements for minimal frequency and AFC stability. Based on experiment, it was found out the minimal characteristic for monitoring and analysis are frequency band from 10 to 10,000 Hz, bandpass flatness -3 dB on from 10 to 100 Hz. Based on technical requirements, the SP Lab USB RTI Meteor Pro edition was selected, presented on a figure. Also on the table show its characteristic. So important to choose the right single-board computer for collecting and transmitting data to the server. Then choosing a single-board computer, we were guided by the following requirements. Ease of development, support for recording in multiple streams, the ability to implement complete remote control over data transmission, multiple USB outputs, low costs. Based on these requirements, we choose a super popular single-board computer Raspberry Pi 3, presented on the slide. It is also very important to choose a suitable data transfer protocol that is capable of transmission data to the server safely, reliable, with sufficient bandwidth. We choose the MQTT protocol. MQTT that the publish-subscribe network protocol that transmissions message between devices. This protocol has the following advantages: packnet agnostic, reliability, scalability, decoupled design, and the time. The exchange of message in the MQTT protocol is carried out between client, the publisher, which is the Raspberry Pi, and the broker of message. This is our server. We will look at the software part. Consider the problem statement for the anomaly detection block, discuss the data transformation process, autoencoder network architecture, the process of initialization, and the online fast working of system. We will also touch on the advantaged analysis block. This slide shows the entry architecture of the system. Sound is recorded in several streams to a microcomputer and sent to a server. Database Manager service monitors data flows, performs data transfer between microservices. The services of calculation the file anomaly indication allows you to quantify the possibility of defect detection. The analysis has shown that for the implementation of such a microservices, the best solution to achieve high accuracy and resistant to noise has a sample that include autoencoders and machine learning algorithms. Advanced analysis servers is the second stage in analysis and diagnostic system. In the current implementation of the microservices include a library of heuristic frequency dependent on the fundamental frequency and algorithms for finding the reference frequency. As a result of the service work, the conclusion about the reason of the equipment non-stationary operation issued. Let's now consider an anomaly detection block. Let's talk about problem statement. Anomaly sound detection is the task to identify the sound emitted from a target machine is normal or abnormal. Automatically detection machine failure is an essential technology in the fourth industrial revolution, including artificial intelligence based on factory automation. Prompt detection of machine anomaly by observing its sound may be useful for machine condition monitoring. The main challenges for this task is to detect unknown anomaly sound under the condition that only normal sound sample has been proved as a training dataset. In real-world factories, actual anomaly sound rarely occur and are highly diverse. Therefore, exclusive patterns of anomaly sound are impossible to deliberately take and or may collect. This means we have to detect unknown anomaly sound that were not observed in the given training dataset. Some detail about this problem, about this task, you can find at the competition the case 2020. Our anomaly detection block is a service of audio track anomaly assessment based on autoencoder. An autoencoder is a type of artificial neural network used to learn efficient data coding in an unsupervised manner. The aim of an autoencoder is to learn a representation for a set of data, typically four-dimensionally reduced, by training the network to ignore signal noise. Along the reduced side, a reconstruction side is learned where autoencoder tries to generate from the reduced encoding a representation as close as possible to its original input, since its name. This termination itself is calculated as the difference between original sound and the sound reconstructed after autoencoder. To obtain minimal anomaly values for sound with normal operation of the rotor machine, autoencoder trains to minimize the error of restoring normal operation sound. This method assumed as autoencoder cannot reconstruct sound that are not used for its learning. This approach has described in this paper and has proved to be effective. Data transform. The original sound wave transformed to log-mel spectrogram. The resulting image X is fed into autoencoder input, when the acoustic feature as T is obtained by concatenating before after several frames of log-mel feature bank output as phi sub T. All transformation you can see on this picture. This task is evaluated with the area under the received operating characteristic curve, ROC-AUC, and the partition AUC. The partition AUC is the AUC calculated from a partition of the ROC curve over the pre-specified range of interest. In our metric, the PAUC is calculated as the AUC of a low false positive rate range. An AUC and PAUC you can see there. H is a flooring function, return 1, then this difference more than 0, and return 0 in other size. N sub plus and sub minus is a normal and normal test samples, respectively, and have been sorted so that the anomaly scores are in descended order. The anomaly sound score function you can see there. Phi sub T, it's original sound spectrogram, and IE sub theta, it's a reconstructed spectrogram after autoencoder. According to above formulas, the anomaly sounds of normal test samples are used as the threshold. This is why participants need to submit anomaly scores of all test samples instead of a decision results. The reason for addition use a partition AUC is based on practical requirements. If an anomaly detection system given a false alert frequency, we cannot trust him, just as a boy who cried a wolf could not be trusted. Therefore, it's especially important to increase the true positive rate under low false positive rate condition. In the task, we use P equal 0.1. The architecture of the autoencoder network is shown on the slide. We use convolution layers because they are better for image-related tasks. Identification of the model. For a short time, the system will record the sound of equipment based on the fact that its operation in normal mode. This data will be used to teach the anomaly detection mode. This stage is called normal identification phase. After receiving the model, there is an online part, there is streaming mode, the sound of the equipment operation and recording in the anomaly search block, and each model will have its own status. Anomalous recording go to a block named Advanced Analytics. The advanced analysis block is a responsibility for finding the defect that causes when acoustic data anomalies. This analysis is based on certain frequency heuristic dependence, in most cases the analysis being with the determination of a main frequency. This task is complicated by the strong noise of the spectre. Then diagnostic use acoustic signal. An important factor is the amplitude frequency characteristic of the microphone. In a central case, using a low frequency analysis, in which it's impossible to determine the original frequency of moving, an analysis can only be carried out by secondary harmonic. This block is devoted to the experiment per moment. The setting of experiment, the data obtained will be discussed, and the result of the work of both block of the system. Let's start by watching a video of the data building process and see the system in action. An experiment was conducted to a test of system's operability. The object of monitoring and diagnostic was an electric motor. A motor was recorded at different speeds from 5 Hz to 30 Hz. When wave of different depth, 10, 20, 30 grams, we hang on the desk to simulate the shift run out. The files are recorded for 10 seconds each one. For training was used 1400 record files for normal motor operation. The test sample was the remaining 600 normal operation file and 900 anomalies. You can see the results of the binary classification on confusion matrix, and you can see recall and precision. The anomaly files were moved to advanced analysis block. The spectrogram shows the second harmonics marked in red on the main speed marked in brown. The present of the harmonic indicate the onset of a shaft beating defect. Finding such defendants for all possible defects will allow you not only to identify the cases of defect, but also to predict their occurrence and give a recommendation for operator. As a result of this work, the concept of non-invasive acoustic monitoring was developed. The hardware base for data collection was developed to be sufficiently flexible and easy to install. As a result of the experiment, the diagnostic system shows a good result in identification of the anomalies, shows a good overall accuracy. The correct determination of fundamental frequency is also a problem for our system. It is directly related to the accuracy of the speed determination of the second harmonic coefficients and consequently to the equipment defect. This problem is now solved by setting the fundamental frequency search interval. Further technologies developed related to the data accumulation. By using historical data, it will be possible to implement models for predictive the state of the equipment.